Chapter 8 test is Tuesday next week, right? Next class. Today, we're going to start Chapter 9. So, Chapter 9 is about like three-dimensional geometry ideas. Typically not a super challenging chapter. Section 1 is kind of a nothing burger of a section. We're just going to do a bit of vocab and talk about or review some formulas that you guys saw in geometry. So here we go. So first up, we got ourselves 4 figures. This first one, what do we call that guy? Cube. And then this one?
Rectangular prism.
Yeah, rectangular prism. Overseas, they call it a cuboid also. Yeah, fancy. What's this guy? That's a pyramid, and typically we name a pyramid by the shape of its base. So this would be a square pyramid. And then this little ramp guy over here is that's a triangular prism. So again, prism means that the faces of the figure are rectangles. So there's 3 rectangular faces. And then the 2 parallel sides are called the bases. And we name our prism by the shape of the base. So here the bases are these 2 triangles. That's why it's a triangular prism. So we have that. Really, any 3D shape that has 2 congruent sides that are parallel like that, and the cross section is the same the whole way through, would be considered a prism. Next round of shapes. Oops. Is here. This first one is a cylinder. This is another rectangular prism or rectangular solid. Either name is fine. What do we notice about this one here versus this one? Yeah, it's slanted. So when we have one of those, it's called an oblique. Oblique, like your abdominal muscle. So if it's not if the height of the figure is not perpendicular to the base, we call that oblique. This guy is another triangular prism. And what's this? Yeah, that's a pentagonal prism. So aside from this one in the middle, all of these shapes, the height of the figure is perpendicular to the base. So the name we give for those figures, we call those all right figures. So we'd say that's like a right cylinder or right rectangular solid or a right pentagonal prism. Everybody's cool with that? Okay. So what about figures where the height is not a side length? Right? So let's say we have a square pyramid. So the height is this like internal segment here. So if this is a right square pyramid, that internal segment should be perpendicular to the base. Right? Keep in mind that the height of the figure need not be a side length. It could be like one of these internal segments, like in the pyramid. Everybody's cool with that idea? Okay. As a little aside, what's the most famous oblique cylinder?
Leaning Tower of Pisa.
The Leaning Tower of Pisa, yeah. Another set of figures. So the first one is a sphere, and the middle, or the next one, that's a hemisphere. Half of a sphere is a hemisphere. And we got the cylinder again. This last one is a cone. Specifically, we'd call this a right cone, as it certainly looks as its height is perpendicular to the base, which is the circle. So let's now branch off that we've done some names into some basic formulas that we would have seen in our geometry classes or even prior to that. So we'll start with areas for triangle. So we know from way back when the area of a triangle is 1/2 base times height. But we also, from earlier this semester, we know that the area of a triangle is also 1/2 AB sine C. Both of these might be useful. What's particularly useful about the second formula? We don't need the height, right? Because we know for a triangle, the height is often not a side length, right? The only triangle where the height is a side length is a right triangle. So this one can be particularly useful if you're not given a height or you don't have a right triangle. We have the area of a parallelogram is just base times height. Remember that a parallelogram includes squares and rectangles and rhombuses, rhombi? Yeah, I'm not sure. Grammarians, consensus on that? Nobody has one? That's okay. So the next up is a trapezoid. Anybody remember the area for a trapezoid? It's 1/2 base 1 plus base 2 divided by height, or times height, excuse me. And then you can tell the two bases of a trapezoid pretty easily because those are the two sides that are parallel. Yeah, exactly. And overseas, they call trapezoids trapezium. Yeah, right? Fancy. It's like I'm moving to England. All right. Next set of formulas. Again, all these should come as like at least familiar. It's like, yeah, I'm sure we did that in geometry, whatever. We're just plugging values into a formula, no big deal. Circumference of a circle is 2 pi r. The area for a circle is pi r squared, common to students to goof those. What's the other alternative form for the circumference of a circle? Pi d, where d is the diameter, which is 2 times the radius, so it's the same thing. Either is fine. For a cone, the area for the curved part of a cone is pi r L, where L is the slant height for the cone. So when we talk about the curved surface or the curved area of the cone, we're talking about the not the bottom of it, right? So like radius for the base of the cone is that. And the L is like this side length BC. Now, when I write my letter L's, I usually use a cursive L. Why do you suppose I do that? The lowercase L looks a lot like a number 1, and this is math class, and I write a lot of 1s. Feels like a recipe for me to make a mistake. Okay. So again, that side L is referred to as a slant height, is what we call that. So volume for a cone then is 1/3 pi r squared h. What do you notice pi r squared is? That's the area of the base, the area of the circle, times the height. So this is like 1/3 area of the base times the height. So the area for the curved surface of a cylinder, right? What does that mean? It's 2 pi r h. That's not where I want that to go. Okay, fine. Be difficult. Yeah, so let's talk about that. So if I look at my cylinder there, what sides are flat? The top and the bottom, right? So if I take the sides of that cylinder, those are all curved, right? If I like snip along and unroll that, I'd have like a rectangle where that side of the rectangle is the height of the cylinder. What is this distance going to be? The circumference of the circle, right? Because it's got to wrap around. The area of that rectangle then is 2 pi r h.
So that's only, it's not.
Does not include the bases, correct? Because those are flat. Or at least a flat surface, right?
Yeah.
I mean, clearly a circle is not flat, right? Okay. Okay, some more volumes. So the volume of a cylinder is pi r squared h. Again, what do you notice that is? Area of the base times the height. So like for a figure like the cylinder where there's like no negative space, it's just area of the base times the height. If there is some negative space like a cone, you'll need some coefficient in front of it because you're only getting a fraction of that space filled. Surface area of a sphere is 4 pi r squared, and the volume is 4/3 pi r cubed. So we keep on going. What about a pyramid? Now, pyramid's a little bit tricky because what can change in between pyramids? They can have different bases. So we're just going to call this 1/3 AH, where A is the area of the base. So if the base was a square, it would just be side squared H, or 1/3 side squared H, I should say. If it was a regular pentagon, the area would be different. I think in geometry, you guys find the areas for regular figures. It's been a while. We'll review how to do that a little bit later. What if our volume is for a cuboid, like a rectangular solid, a box? This is good old length times width times height. Right? Yeah, no problem. And in general, whether that prism is rectangular or anything else, the formula is just area of the base times height, right? So in the case of a rectangle, the rectangle is just length times width. That's the area of the base, and then just times height still. So again, most of these formulas are just formulas. They're things you did in geometry. It should be largely review. I skated through all that stuff real fast. The names are just the names. Again, like things that they're shapes you should be familiar with. Vocab we should be familiar with. If that wasn't the case, like talk to me individually. But I think for the most part, those are fairly straightforward things. for sections 2, 3, and 4, we're going to use some PowerPoints to do these because we'll have to generate some pictures, and boy, it's a heck of a lot easier to have those kind of all put together in a PowerPoint than it is to like even drop them into OneNote. Just a lot of dropping. I did a lot of dropping there today, which was also kind of aggravating for me, but it's whatever. So in section 2, we're going to be looking at lengths inside of the three-dimensional solids. So the goal for this, to find a length of a line inside of a three-dimensional figure, we're going to build what's called a calculation triangle. So for example, inside of this pyramid, I might build the triangle ABC and use that as a calculation triangle. In general, when I'm building one of these calculation triangles, what kind of triangle do I want? A right triangle. Why would a right triangle be helpful? You can use Pythagorean theorem, you can use SOHCAHTOA, they're easy to do the areas on. It's the preference is that we have a nice, easy right triangle to work with. Everybody's cool with that? Okay. Now, the trick is that some of these right triangles can be kind of like hidden unexpectedly inside of our figure. This tends to be the trickiest thing inside of this chapter, is just getting good at finding these calculation triangles inside of our three-dimensional figure. So for example, if we take this rectangular prism or cuboid, the pink triangle here is a calculation triangle. That's a right triangle. It should be easy to see that's a right triangle. The blue triangle is also a right triangle. What is the right angle? It's G. The reason I know that G is a right angle is the side GD is inside of this face on the right side of the cuboid, and the side FG is like the height, and I know the heights are perpendicular to the faces, so FG and GD must be perpendicular to one another. Although even though I look at it on a piece of paper, it does not look like a right triangle. I have to use some three-dimensional imagination and think about what it actually looks like in space, and then it's much clearer what's going on there. But that's not a skill that we're used to doing. So if that takes a little bit of time and effort for you, that is perfectly normal. But we need to kind of get good at kind of stretching our three-dimensional imagination. That'll be quite helpful in this chapter. Let's do another one. So let's say we have this triangular prism. Again, the pink triangle, I'm guessing that nobody has any trouble seeing that that's a right triangle. Angle F certainly looks like a right angle. The blue triangle, though, is also a right triangle. Which one is our right angle? B. Good. And again, we know it's a right angle at B because the segment BG is a segment inside of the base of our prism. BE is a height for the prism, and I know that the heights are perpendicular to the faces. So I know that angle B in the blue triangle is also a right angle. And again, if you think about that in 3 dimensions, that checks out, but you need to use your imagination a little bit to see it. It's not natural. You look at the sheet of paper and it doesn't look like a right triangle on the sheet of paper until you kind of squint at it and see it in 3 dimensions, and then you're like, okay, I got it. But that can happen faster and easier for some of us than others, and that's okay, right? Just if it's not easy for you, just put some time and effort in and you can get it. One more. So let's say we have this pyramid here. Blue triangle, pretty easy to see that that's a right triangle, that angle F is a right angle. The pink triangle, also a right triangle. Angle F in the pink triangle is also a right angle. Again, I know that EF is the height for the pyramid. I know that's perpendicular to the base. So any segment in the base, including AF, has to be perpendicular to the height. Is this going okay? And I'll post all these PowerPoints into My Notre Dame or something here later today. I just haven't had a chance to do it yet. You don't have to worry about copying anything down, right? Because drawing these pictures is like totally unrealistic by hand, right? I couldn't do it. Oh, I could. I mean, it would take me a long time, though. Not feasible to do it inside of my notes that I'm supposed to be just kind of going quickly on. All right, so let's run through some examples. So suppose we have some box that's 32 long, 18 wide, and 11 high, and we want to find the length of the longest rod that we would fit inside of this box. So use your imagination a little bit. How are we going to fit the longest thing possible inside of this box?
Find the distance between two corners using like a side points.
Okay. You could do that. Joe?
So you make a right triangle from one of the corners of the base all the way to the opposite corner and up to the top.
Yeah, so it's going to be like bottom back to front top is going to be the longest segment we could fit in there. So the plan to do a problem like this, we're going to sketch a picture. We're going to identify the calculation triangle or triangles that we need to solve this. Sketch and label those calculation triangles and then solve. So we'll start with our picture. So there's our box. So our longest segment, for example, could go from like A to G, or like F to D, or E to C, from opposite sides, top to bottom. So the one I drew was AG. And the calculation triangle that I'm going to use is going to be the triangle ACG. What's the problem, though? To solve a right triangle, I need to have three things. I need to have the right angle and then either two sides or a side and an angle. What do I have? Just one side, right? So I'm either going to have to find angle G, angle A, or side AC. I'm going to assume that I can't find AG directly, or else I would have not chosen this as my reference triangle, right? Or calculation triangle. So which one of those three do you feel like is going to be the easiest to come by? Angle G, angle A, or side AC? Side AC should be your answer. Why not one of the angles? You don't have any other angles in the picture, do you? Right? It seems really not very simple to get at that. Okay, so I'm going to make a second calculation triangle to find the length for AC. What calculation triangle would I do? ACD, yeah, so this one down here. So to find AC, I use Pythagorean theorem. I get the square root of 1348. I can then plug that value into my pink triangle. The square root of 1348 is this 36.7. Just it was easier for me to put it as a decimal than to get the square root to go in. And now I can do the Pythagorean theorem again. Notice when I did that, I used the square root of 1348. And so the value for AG that I get is 38.33, approximately. Everybody's okay with this? Again, once you see it done, fairly simple process. The hard part is, like, again, identifying those calculation triangles that you need to kind of do it. But the actual arithmetic that we're doing is really simple, right? Just Pythagorean theorems over and over again, right? The algebra is real simple, though. Let's do another example. So let's say we have a square-based pyramid. So E is the top and then ABCD is the base. The sides of that square are 12. And the height of the pyramid is 9.5. We're going to calculate first the length of EC. So that's just like one of those slant heights for the pyramid, so like one of the edges of the pyramid. And then we have a point M that's halfway along one of the sides of the bases. We're going to calculate EM, so that's like down one of the triangular faces, like the height of one of those triangular faces. And then talk about why they are not going to be the same length. So we'll start with part A. I'm going to start by drawing my picture. I drew the calculation triangle EFC here. Again, what do I have? A right triangle. Do I have enough information to solve EC? No. What other piece am I going to be needing? FC. To calculate FC, what other triangle would I use?
Yes.
Well, I'm going to use ACD. I'm going to use this one. Because what is the relationship between AC and FC? Yeah, FC is half of AC, right? How do I know that? I mean, it looks like it, but how do I know it?
It's in height on the top.
Yeah, so the point F, if this is a right-based or square-based right pyramid, we know that this is a right angle. So that's got to be directly in the center of the square there. So it's going to be on all the diagonals will bisect there. So that's quite helpful. So there's my triangle ADC. So I can use the Pythagorean theorem to find the side AC, which is just root 288. And then I can observe that FC is half of that. Now that I have FC, I have everything I need to calculate EC. So I can just plug that stuff in. So EC is EF squared plus FC squared. So I get 12.74 for that. For part B, we're going to mark a point M halfway along one of the sides of the bases. So there's my M. And then we're going to find the length of EM. So the calculation triangle I drew in here was this EFM. Do I have enough information with EFM to solve for EM? No, what would I need? We know the height is 9.5. FM. Do I really need to find FM though? What's the length of FM got to be? Half of a side length, right? How long are the sides? 12, so FM is 6. We really did have all the information we needed for this one, right? We didn't need a second triangle. Now, you could have built a second triangle to do this, but like, shoot, man, that's some overkill. All right, so now I can just Pythagorean theorem it up. I get 11.4. Remember the previous one was 12 point something or another. Notice these are not the same length. So like, why not? What's a good geometric explanation for why these had to be different? I'd say there's two appropriate arguments you could use here. Well, the first argument would think is feasible, or the obvious one is, these are both the hypotenuse of two different triangles, right? One triangle's height is 9.5, but the other leg, FC, is a different length than FM. Can't have a hypotenuse be the same if both leg lengths are different, right? Or if one leg length is the same, but the other is different. That's a reasonable argument. The other argument that I think is also reasonable, look at the triangle EMC. In that triangle, it's a right triangle. EM is like a leg, and EC is the hypotenuse, you best not have a right triangle whose leg length is the same as the hypotenuse, right? That ain't going to happen either. So I think either one of those two arguments are good arguments as to why those could not be feasibly the same length. Everybody's okay with that? So again, there we go. All right. Hi, welcome back. Here we go. I think this is the last example, I think. So we have a cone here. We're told that the side AB is 11.3, and angle ABC is 53, and we're asked to find the radius of this cone. Do we have the information we need to fill in our calculation triangle BDC? Well, what can we fill in? Yeah, we know that the length of BC is the same as the length of AB, so that's 11.3. Now we know that angle ABC is 53. Does that allow us to say anything? DBC is half of that. Why? How do you know that it's gonna bisect it? This is a specific geometry theorem that we're looking for here. So this is what kind of triangle is ABC? Okay, what else other kind of triangle is it? If you classify by side lengths. Isosceles, yeah. In an isosceles triangle, the angle-based bisector for the apex is also a perpendicular bisector of the other side, and vice versa. So I know the perpendicular bisector here is also an angle bisector up here. This is not true if you don't have an isosceles triangle. Okay? So if this cone was oblique, where one side, like it was tilted, and one side was longer than the other side, or one leg was off, I guess I can't call them legs anymore. If one of the slant edges was a different length from the other, we could not do what we just did. Everybody's cool with that? Very common mistake for students to just think that you can just bisect things when you drop in altitude in non-isosceles triangles. But you're right. So how do we solve for side R now? What's that? SOHCAHTOA, yeah. Specifically, which one are we going to need? Sine, yeah. So sine of 26.5 is equal to opposite over hypotenuse. Solve for R, 504. What do you notice about the mode that your calculator should be in? Degrees. For the whole chapter, degree mode would be what you want. If you haven't been in your calculator in a while, you might want to double check to make sure it's still in degree mode before you dive in on the homeworks. So far, so good? Pretty easy. By and large, nothing really complicated going on. It's just visually a little bit tricky, but that's the worst part of it. The algebra is like quite easy. This is where we're going to stop. We'll do sections 3 and 4 next time. At this point, you can do up through question 7 in the problem set. After that, you start getting angle questions in there also, but like, there's no reason you couldn't keep going and do some of these angle problems if you're so motivated. It's not decidedly different than doing anything inside of a right triangle. It's going to be the same idea, just you're going to be using like, have to break out like a sine inverse or something. Oh my gosh. But that's kind of the gist of it. We're only assigning 1 through 7 today. The rest of the class, you can continue working on your chapter 8 problem sets or reviews. If you have chapter 8 questions, you can ask me about that stuff individually. Or if you're ready to start the chapter 9 homework because you're like, I'm all caught up and good to go on 8, then start on the chapter 9 stuff. You know what I'm saying? For Sunday, you guys are looking at 89 through 122, and then the review would be the assignment. Sound good to you guys? All righty. I'm stopping this and getting out of your way and letting you get crack-a-lackin'.